Let's explain flux by measuring it. In the context of light metrics, flux is the light power per unit area. Given a constant source of power, the more you spread out that incoming power, the lower the flux. This has important implications in astronomy, as it explains how sunlight shining on Earth, known as insolation, heats the surface differently depending on latitude. Near the equator, solar power hits the surface more directly, hence it is more concentrated per unit area and there is greater heating. Far away from the equator, solar power hits at an angle, is spread out over a larger area, and hence there is lower flux and less heating. Combine this with the tilt of the Earth's axis, and you get an explanation for the seasons. Here is the mathematical treatment. Suppose we have incoming light that hits an area A0 perpendicular, and we measure a flux F0. Now let's tilt that same area away from the perpendicular to the incoming light by angle theta. We have thus reduced the effective cross-section or equivalent light collecting area. The flux measured will be reduced as the cosine of the angle. Another way of understanding cross-section is thinking about collecting rainwater in a bin. When the bin's top is perpendicular to the incoming rainfall, you will get a greater rate or flux of rainwater collected. If you tilt that area, then it is not used as efficiently as less rainwater is intercepted by that same area. Now, I will demonstrate this principle using real photometry. For the hardware setup, first of course, you need a standard light source. We will use a 100-watt light bulb in this example. You will need to establish a distance of about 1 meter from it, where you will make the measurements. You will need a standard surface that is highly reflective, on which you are going to make the measurements. For the electronics, you will need the GLX unit, powered, connected to the light sensor that is set to medium sensitivity, and you need a USB connection to a laptop that has the appropriate capstone software. When you open capstone, make sure it has recognized the light sensor. Choose classic templates, table and graph. Select measurements, time, and relative intensity. Select relative intensity for the graph as well. When you make the measurements, try to stay at the measured out 1 meter distance and start the measurements with the target perpendicular to the incoming light before slowly altering it and then compensating for that change in distance. Notice there is a slight offset in the setup due to the fact that we don't want the light sensor itself to block the incoming light. As expected, the more I tilt the target away from the perpendicular to the incoming light, the lower the flux measured. Let's see this again, but now with more precision from the side. You can now go back and attempt to match up what's happening in the graph versus the angle of the target board. Greater precision is not going to be demonstrated here, but it would involve more precise setup of the angle as well as multiple measurements at each of those angles.